First problem has permutations from the set numbers 1 through 7 to itself, to the set numbers 1 through 7. And there is one requirement, phi of 1 equals 1, and there are 5 rules. Phi of 2 cannot be 5 or 7, phi of 4 cannot be 2, 5, 6. And so I'm referring to this requirement as like sort of the positive rule that it has to be true. You need that to happen, and then the rest are rules that you can't break. There's a distinction that makes this one the one we should consider first, and then the others we can do subtraction and inclusion exclusion to deal with them. So first of all, if phi of 1 is equal to 1, it's nice to have a little picture in mind. Here's a picture of a string diagram. 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7. Those are the numbers 1 through 7. And the numbers 1 through 7 again down here. And if I was going to draw a string diagram of them, phi of 1 equaling 1 means that I have to have that input and output right there. And then you see the rest can be filled in any way you want. Of course, then we'll have to subtract off the rule breakers. But for 2 through 7, there's 6 more dots to connect, top to bottom. And so that'll be counted the same way as if it was permutations on 1 through 6. In other words, we start off with the total being 6 factorial. Even though it's from 7 to 7, because of that requirement that phi of 1 equals 1, really all we have is 6 factorial. All right, now we need to start subtracting. So with these kind of problems, the rules that we're talking about are all going to be very similar. The rules that can't be broken, they're going to be not equal to. So phi of 2 is not equal to 5 or 7. That's a little shorthand I'll use sometimes so that it's easier than writing phi of 2 does not equal to 5, and phi of 2 does not equal to 7, and phi of 4 does not equal to 2, and so on. So this is saying that neither of those can be true. Phi of 2 is not equal to 5, and phi of 2 is not equal to 7. Now, I count how many things I'm not allowed to have. I'm not allowed to have 1, 2, 3, 4, 5. So there's 5 single, no breaking rules not to be broken. Now, I need to subtract ways of breaking one rule. And in fact, I'd be subtracting the set of all, or I'll be subtracting all the sets of permutations that break one rule. Now, if you break one rule, I might as well use this picture since I've got it. Like, here's a 5. If I send phi of 2 to 5, like that, that would be breaking this rule, phi of 2 is not equal to 5. Then I've actually put in another string, and now there's 1, 2, 3, 4, 5 on top and bottom left to fill in. So every time you break one rule in a permutation, there will be one less open input and outputs to connect, and that means you'll count it with one less factorial than the total we started with. So what we said there was that there's 5 rules, and after breaking one of those rules, you'll have 5 factorial ways to fill it in. So each of the sets of breaking one rule will have 5 factorial items in it, and we're subtracting off 5 of them. So just to fill in some there, this would be the number of ways to break one rule. And 5 factorial is, for each way of breaking one rule, how many permutations are in there. So we could describe that as, I'll run out of space if I describe everything. 5 factorial is the number of permutations which break a specific rule once. So we have 5 collections of 5 factorial each. That's why it's minus 5 times 5 factorial. Okay, now let's think about the inclusion-exclusion. So we're subtracting all the single sets, ways to break one rule. Then we'll need to add back in the intersections. Those will be all the ways to break 2 rules. Then we'll subtract the ways to break 3 rules and add back in the ways to break 4 rules. And finally subtract the ways to break all 5 rules. So we're expecting to have minus plus, minus plus, minus plus, where minus will be breaking 1 rule, then 2, 3, 4, 5. We're alternating plus minus. So the next one will be plus, and we want number of ways to break 2 rules. And thinking ahead, once we know the number of ways to break 2 rules, I'll put it here. Once I've broken 2 rules for a particular set of permutations that break 2 rules, 2 specific rules, there will be 4 factorial ways to finish it. To visualize that, pick a couple of rules. Phi of 2 is not equal to 5, and phi of 4 does not equal to, here's 4. Phi of 4 does not equal to 6. So here's a permutation that obeys that original requirement, and it breaks 2 different rules. It breaks phi of 2 equal 5 and phi of 4 equals 6. Then there's still 4 dots left on top, 1, 2, 3, 4, and 4 on bottom, 1, 2, 3, 4 to connect. Oh, well. See, I should actually number these. I was going to send 4 to 6, so that's better. Okay, now it's correct, or now it's doubly bad, whichever way you want to think about it. Just I'll leave this one as a picture and label it. This breaks 2 rules. All right, so how many ways can you do that? And for every one of them, there will be 4 factorial ways to finish the permutation off. So that means there will be 4 factorial permutations in that collection, and that'll mean we can multiply 4 factorial times the number of ways to break 2 rules to count them all at once. Well, to break 2 rules, there's not too many ways to do that on this problem. Luckily, we have only 2 inputs to worry about. To break 2 rules in a permutation, you have to break 2 different input rules. You can't break these 2 rules at the same time, as in you can't send phi of 2 to 5 and phi of 2 to 7, because then that wouldn't be a function anymore. So the only way you can break 2 rules is if you break 2 input rules. So luckily there's only 2 inputs involved in the rules that I need to worry about breaking. So there's only going to be one possible way to break 2 rules involving 2 inputs, and I just need to draw one tree to figure out how many ways there are. I'll put that in words. Only 2 inputs involved in our 5 total rules. So 2, there's only 2 inputs, and I need 2 choose 2 equals 1 tree to draw. in the next example, there will be a bunch of trees to draw because there will be more than 2 inputs involved. This time there's only 2 inputs involved. I need to break 2 rules. So it was 2 inputs, choose 2 rules, or choose 2 inputs. And that gives me 1 tree to draw. All right, here's the tree. So first I break the rule involving input 2. So input is in the little box. Output I write on the branch. So the way to break break 1 rule there involving input 2 is to make it a 5 or a 7. I picked 5 in the picture, but another way to break it is to send the string to 7. Then the second input is 4. So for that, to break the rule, I can make 4 go to 2, 5, or 6. However, I can't use a number I already used as the output. So for instance, on this first one, I can have 2 or 6 as the possibles. Can't very well put a 5 there. If you do, you should cross it off. It's not allowed to put 5 twice on these options because the permutation is 1 to 1. I can't send 2 to 5 and 4 to 5. That's no good. I can send 2 to 5 and 4 to 6. In fact, 2 to 5 and 4 to 6 would be this picture up here. Okay, if I send 2 to 7, however, on this option down here, then all the options for sending 4 are still open. So I'll have 3 possibilities there. That 2, 5, and 6. Alright, so I'll put some little leaves on the end so they're easier to count. And that's the only tree I have to draw. There's only two places where it branches. And at the end I see 1, 2, 3, 4, 5 total ways to do it. So the number that goes there is 5. That's the counting those right there. All 5 of those. Alright, then I should think about minusing the number of ways to break 3 rules. But we already said there's no way to do that. I only have 2 inputs that have not equal requirements or rules that it can't break. And there's no way to pick 3 of them because there's only 2. You can't pick 2 of the three outputs because then I'll be forced to use 2 of them from 1 input. So there's a 0, number of ways to break 3 rules, and number of ways to break 4 rules would be a plus. That would be the 4 rules. You know, if you can't break 3, you can't break more. And then finally 5 would be 0 as well. So I just showed those to show that those possibly could have numbers in them if it was a different kind of a problem. But in this one, they're all going to be 0. Alright. And I did put this on the paper as well. And on the paper I calculated it out. You could almost do this one without a calculator. A calculator is fine too. You've got 6 factorial, which is 720, and it's almost minus another 6 factorial. But it's minus 5 times 5 factorial instead of 6 factorial, 6 times 5 factorial. So it's like you get 720 minus 5 times 120, so minus 600. So that leaves you 120. And this is plus another 120, 5 times 4 factorial. So you get 240 total. answer.